Well, thanks for having me, first of all. Um, my name is Alon, Albalak. So I'm a student, obviously here at UCSB in the computer science department. I'm a fourth year PhD student working with Professors William Wang and Shifeng Yan. And my area of research is natural language processing. So for those who aren't familiar, natural language processing is kind of a subfield of machine learning, where what we try to do is try to get machines to be able to understand human language, English or any other language, really, whether that's an existing language or I mean, an alive language, or even some languages which people don't speak anymore. Trying to understand ancient texts and that kind of stuff is also part of natural language processing. So, as I said, natural language processing is a kind of a subfield of machine learning. So, what is machine learning really, though? If you've probably heard of machine learning, and it's kind of everywhere. If you read in newspaper articles, if you anything in the tech area, every day there's new articles talking about all these different topics of machine learning and big data and data mining and all these kinds of things. And this is very common. It's it's very it's kind of like a sexy area of computer science at the moment. So there's lots and lots of different things, lots of information about it. But what is it really? So machine learning is kind of this design and analysis of algorithms where we want to design these algorithms so that they can improve their performance on their own. They're going to be given some sort of task and some data to use as their experiences, and we want them to be able to learn without our too much of our own input. And the way that this works really is that what we give them, as I said, we kind of have experience, and the way that machines can experience things is by seeing data. They get some sort of input, and we tell them, here's the input, here's the desired output. And what we would like to have happen is that we're going to use this learning algorithm. Sorry, let me just get my laser pointer on. What we want to do is give the learning algorithm the data, and the learning algorithm is going to decide what to do with it. That way we have a little bit less, we don't have to make manual decisions and say, here's how you should analyze the data or anything like that. Machine learning is the idea where this learning algorithm is going to do all of the heavy lifting. It's going to try and determine what this data means, and it's going to try and turn this data into knowledge. And this is an iterative process. What's going to happen is that the learning algorithm is going to see the data, and it's going to learn some things, it's going to make some mistakes, and then it's going to take those mistakes and going to feed that back into the data, and it's going to be able to repeat the learning process, and it's going to improve over time. That's the idea. And generally, what we've seen in the past 10 to 15 years, probably even longer, is really that with modern machine learning algorithms, more data generally is better. It's going to get you more experience in similar ways to how humans who get more experience will have more knowledge about that task, and they're going to be able to perform better. And this learning algorithm itself could be something where we're going to do all the learning at once and then deploy this learned machine learning model as is. So that could be in something like a face detection where, okay, suppose that we have a whole bunch of training data with faces that are outlined, and the learning algorithm is going to train a machine learning model to be able to recognize those faces, and then we're going to use that in whatever, for Snapchat or whatever app it is that we're trying to make, let's say. This process, though, could also be happening online. It could be in a situation where we're going to be able to gather more data as we go. So this is an example of this online learning is something like predicting stock prices, where we really kind of need to know the future in order to be able to get this data and this experience. So the way that we can emulate that is by saying, okay, we would like for our model to predict what is the stock price, let's say, of a specific stock in 5 minutes. And in 5 minutes from now, we're going to know what the answer is. And so we can learn, or the machine learning model really can learn in this iterative process by just waiting for what the future is. And that's kind of an example of this online learning. So the big picture of what machine learning is and what the purpose is and why this is useful and why people care about it is really just that we want these machine learning models to be able to solve problems with this data. We're going to gather some data. We want them to be able to solve problems. Sometimes solving problems means that they give us the final answer. Sometimes it just means that they're going to help us understand the data a little bit better. And the answer really then is just some information that's going to help us humans to make a better decision. And this is a really nice little graphic that kind of explains they call it the DIKW pyramid, which is on the x-axis we talk about understanding, on the y-axis we have connectedness. And really it just means that what we would like to have happen is that we're going to have a model that's going to convert this data into as it moves up in kind of abstractions from the data, it's going to be able to pull out some relations between pieces of the data. So maybe some words are related, or it's going to understand that maybe some characters within words are related. So there's specific patterns that it finds, and it's going to be able to connect those relations into patterns. And then it's going to be able to connect these patterns that it understands into something even bigger. And kind of moves up into this area of wisdom, where it's going to be able to understand big picture principles. Things like, it's not just understanding what a word means, but it's going to be able to connect words together. And once it understands the words, it's going to be able to understand that someone's asking a question. And then once it understands that someone's asking a question, it's going to be able to go and look for what is the answer to that question. And this is kind of the big picture of what we really want from machine learning. So there's a lot of applications really of machine learning, as we can see. So some of them are things like search engines, where kind of what I just explained is that if someone's going to put in a question, they have a query, and what we want to do is we want to be able to pull the most relevant documents. So things like, it could be just an answer sometimes, which Google actually does that now. They have a little box on the side that if you ask a question, it's going to try and find the answer to that exact question in Wikipedia and pull that out for you. But search engines could also sometimes, a query doesn't necessarily mean a question. It could just be that you're interested in finding relevant information to whatever it is that you're interested in. There are also things like bioinformatics, where supposedly it can analyze maybe some patterns of the ways that a specific bacteria or virus or yeast or something, the way that it replicates. And we're going to try and pull out some patterns that we see from there. Maybe what we want to do is learn something from one species of yeast, and we want to try and understand why does that species do some specific or have some specific characteristic. And what we want to do really is then understand what is it that's causing that characteristic. So these are kind of applications of machine learning, where what we want to do is pull out some patterns from data. And that's something that sometimes it's very, very hard for humans to do that, just because the data itself is not well organized, or maybe it's just huge amounts of data. Or the patterns themselves aren't, maybe in a genome, it could be thousands of proteins that make up a specific genome, and it's hard for humans to really capture that pattern at in our own memory. And obviously, there's tons of other applications of machine learning in things like detecting credit card fraud, or as I talked a little bit about stock market analysis, or especially in like robotics. There's lots of machine learning that happens. Or like in game playing, like AlphaGo, or like in StarCraft 2. I forget who it was. I think OpenAI had their machine learning model that learned how to play Dota. Also in software engineering, machine learning is very applicable. It's similar actually to natural language processing. I don't know if anyone's heard of OpenAI has, GitHub has Copilot, which is essentially, it's a machine learning model that has read thousands and thousands and possibly millions of people's GitHub repos and learn to predict. Suppose that you type a comment and say, I would like my code to do, run a for loop over some specific iterable. And the model has learned that, okay, given this English instruction, here is the Python code that will do that. And this is a very applicable use of machine learning, actually. So before we talk about machine learning, it's pretty important actually to think about how do humans learn, and trying to understand how do humans learn, and then think of how can we get machines to learn. That's kind of the inspiration for how can machines learn. So some of the ways that people can learn is through just memorization. So when you were a kid, if you had to learn your home phone number, there's not really any way of practicing it other than just looking at it. You see the numbers and you just memorize it. It's the only thing that's possible. But you can also learn through conditioning. So an example would be like when you were a kid, if your parent comes home and they kind of have a stern look on their face, you've probably over time learned to associate a stern look with, uh-oh, I did something wrong. Maybe they saw that I spilled the flour everywhere, whatever, something happened. Or sometimes we can learn from specific instructions. Someone can tell us exactly what it is we need to do, like the directions to get from point A to point B. Or we can learn from explanations where they can generally explain how it is that we're supposed to do some process, or from advice. Sometimes we can learn from seeing people do things, or we can learn by doing ourselves. And that's very similar to exploration and discovery. And also we can learn by analogy. So an example would be, if you know how to play soccer, you know how to kick a soccer ball, but you're trying to learn how to kick a football. The way that someone could explain to you how to perform this new task that you haven't done before would be by relating it to some task that you've already learned how to do. They would say, oh, it's kind of like kicking a soccer ball, except you do something a little bit differently. So the standard machine learning problem, there are some very typical problems, is how I would call them. And what happens is that we're just going to be given a bunch of examples, and that's our training data. That's how the model is going to learn. That's how we're going to train this model. And then we're going to use this trained model to be able to predict something new. So we're going to use some new examples that we didn't train on. We're going to ask our machine learning model to predict something about these new examples. Some very common examples of these really standard machine learning tasks would be something like filtering out spam. So everybody has a spam folder in your inbox, and it's very easy really to gather this data. All you have to do is just you get a whole bunch of emails. You have somebody who labels it and says, this is a real email, this one's spam, this one's real, this one's fake. And then what we do is just, as I've kind of hinted at, so we have this training data, we have a whole bunch of examples of emails that are spam, we have a whole bunch of emails that are real emails, or ham is what it's called. And we're going to train the model using a whole bunch of examples. And then what happens is that in the real world, in our inbox, the machine learning model has already learned everything it's going to learn. And it's just now going to predict whether these new emails, it's never seen this email that you just received, but is still able to predict whether it's spam or not. And maybe not 100% of the time, but they probably, for the most part, they do a very good job, actually. And these are just some other examples of just very typical machine learning problems, things like face recognition, or making in any of these decision-making processes like chess, where you have to make a move, and then you're going to learn, was that a good move, was it a bad move? You're only going to learn that later on. And kind of in this iterative process, you're going to be able to learn. So some of the questions about machine learning are the ways that these problems differ are in when does the learning take place. So things like spam filtering, as we said, this is something that takes place well before any email has made it to your inbox. But chess is something actually that, as the machine learning model plays the game, it can get new feedback. And so it can continue to learn as it plays. Another question is just how frequently is the model updated? So things like spam, if you just have one machine learning model and you trained it 10 years ago, well, the people who write spam emails are going to learn, okay, what does this machine learning model filter out? And they're going to be able to figure out how to get around your spam filter. So you don't want to have this stationary model that never changes. You do kind of want to update your model with any new spam that comes out, or new techniques of ways to get around your spam filter. So just some kind of examples to get us in the mood of machine learning. So suppose that we're given this number sequence, and we're asked to predict what is the next number. You probably would say, okay, so it's 1, 2, 4, 8. Okay, it looks like it's doubling every time. So maybe the next number will be 16. Or if we look at this sequence, we say 3, 4, 5, 2. Seems kind of random, honestly. Or if we're asked, is this image in the same class with this image of the car, in the same class as these images of all red cars? And these seem fairly straightforward, but it kind of depends on the context. Because if I tell you that the answer is 20, and that it is related to this sentence down here, all of a sudden we're given new information, and we found a pattern that maybe humans wouldn't have thought of. But if we look closer, we do get some more information, and we can figure out that, okay, well, the first number in the sequence is 1, first letter of the sentence was A, the first letter of the first word. If we look at the second number is 2, the first letter of the second word is B, and then we see 4, D, 8, H. And then we figure, oh, well, maybe this is actually related to the first letter of each word. And that's exactly what it is. It's just the position in the alphabet of the first letter of each word in the sequence. And similar for the second one, we have, okay, if we're given this extra information and told that the pattern is related to the second piece of information, we can see that actually, okay, each number in the sequence is every other number from this bottom sequence pi. So these are kind of just examples of ways in which maybe a pattern exists in data that doesn't necessarily pop out to us super easily, but it definitely exists. We know for sure it's there. It's just, you need to put it in context. And that's exactly what it is. The problem itself kind of depends on the task and the context within the task. So what is a learning problem? Let's kind of get into the details now of machine learning and the tasks themselves. So the learning itself always, what we want to do is that we want to improve performance on whatever the task is, right? So we have to have some goal, some thing it is that we're trying to do. So suppose it's detecting whether something is spam or ham, then that is exactly the task. We want to classify emails as either spam or ham. We also have to have some experience. We have to have some way of improving on just some baseline predictions. If we just predict uniformly across all the possible labels, that's not very good. What we need to do is we need to have some data that's going to give us information for how to make a better educated guess than just a random guess. And finally, we also need to determine how exactly are we going to know whether we're doing well or are we doing poorly. And that's oftentimes associated with the data where, for example, in this spam versus ham setting, what we want to do is we have labeled data. We have data where we know the email, we have the email and we know what the label of each email is. We know whether it's spam or it's real. And if we do have that, then we can say, okay, well, as long as my accuracy or my F1 score or something like that is high, then my model is doing well. But there are some tasks where that's not so, it's not so easy. It's not a classification task. For example, with checkers, how do you know whether you're doing well? The only way you know whether you're doing well is if you won the game or didn't win the game, but that's not really detailed. Because sometimes maybe you've lost 5 games in a row, but you've still actually improved. Maybe you've learned some new techniques. So yeah, as this example talks about, if the task is playing checkers well, then sometimes you would have some labeled examples. You would have like a series of moves, maybe that some professional players or regular people have played, and that would be labeled data. But also you can extend into this idea of self-play, where the machine learning model is going to play against another version of itself, and it's going to kind of learn to improve over time. And again, sometimes it's very clear how to determine what the performance of a machine learning model is, and sometimes it's not quite so clear. But in this case, the real end goal is that we want to see that we're winning games. Oftentimes, though, we can include other performance measures that include some things that are a little bit smaller scale rather than just winning the game. It would be, okay, did you, how many kings did you get in checkers, or whether you jumped over the opponent's piece or not. And a lot of times the way that this, the learning problem is designed is really based on what we want to be learned and how can we represent the problem. So the components of the learning problem itself, as we've talked about, there's the task, there's the data, and there's how do we determine whether our model is doing well or poorly. So the task is always going to be, it's this behavior or the problem that we're trying to solve, and what are the rules of this problem that we're trying to solve, what structure exists there. So for example, for classification tasks, the task is very simple. It's very straightforward. It's just decide, spam, not spam, very simple. Object recognition is a little bit more complicated because it's not just decide yes, no, it's more of like a where in the picture is this thing, if it exists at all. And it becomes even more complicated when we're talking about robots or reinforcement learning for people who are aware. It's this idea where we're going to have some agent that is acting in either a real or a virtual environment. So that could be an example, chess or playing checkers or chess. would be an example of, we have an agent that is interacting in this environment where it's not the only thing that exists. Sometimes there are other, there's an opponent, sometimes there are teammates, and there are rules that exist in that environment to structure what are the possible things that the machine learning model can do. There's only certain possible actions that it can take. And the data itself is just going to be, as we've said a few times already, it's basically just the way that the machine learning model is going to improve upon itself. It's the learning algorithm is going to try to use this data or the experiences to most efficiently improve the performance of the machine learning model on whatever our desired task is. And the way that we measure the performance, as I've kind of alluded to, is that we're going to, depending on the task, we're going to try and see whether we've improved the accuracy, supposing, of a classification model. Or maybe sometimes we don't just want to be able to solve one task, but actually we want our agent to be able to solve multiple tasks. And so maybe our measure of performance is that we want to see that our machine learning model is able to do some level of goodness for multiple tasks. And how do we determine that each of those tasks is good? Well, probably we would look back at a more simple version of how to determine whether the machine learning model is doing well. Or maybe sometimes we just care about whether we can make a prediction very quickly, or maybe not just the prediction very quickly, but the learning process itself. We would like to have, we would like to see fewer examples and still be able to get to some desired level of accuracy. And actually, in reinforcement learning, oftentimes what we want to see is that we want to see the machine learning model we want to see that it's able to explore. It's able to explore its environment. And even though maybe we give it a few examples of the desired actions and the desired outcomes. So if we're playing a game of chess, we're going to give it a couple examples maybe of how someone has won games of chess in the past. But we don't want it to just be limited to just the examples we've given it. Oftentimes, the idea of machine learning is that we want it to find things that maybe we didn't quite realize were there. We want it to learn new moves in chess and discover new things. And even in bioinformatics or genetics, we want it to learn to be able to predict new structures or new sequences. So depending on the task, there's so many different things that happen in a learning algorithm, and it's all task dependent. It depends on the data that we have and what we're trying to do. So some of the things that go into the process of the machine learning model learning, and some of the things that we as humans can add, and the way that we can formulate it and structure it based on what we know, is that we can include some of these things like prior assumptions. So for a game of chess, we know that there are specific moves that are allowed. So we're not going to allow a machine learning model to do something to make an illegal move, because that doesn't make any sense. Some of the other things we have to consider are, what kind of data do we have? Are we limited? Do we only have a few samples? Do we have lots of samples? Is the data going to be images? Is it going to be spoken language? Is it going to be written language? Or is it going to be experiences, like this model that's playing chess? And also, how do we represent the data is a big question. Many times it's fairly clear, because there's only limited ways to represent a text, for example. But a lot of times what happens with machine learning is that we're not just trying to directly predict the output, but maybe what we're trying to use a machine learning model for is to learn a representation for the data that is in a vector space. So this is actually something that comes from natural language processing. I'll give you guys not a too detailed example, but a very big change in the field in natural language processing that happened recently, the past couple of years, is being able to represent text in a vector space. Basically just a series of a fixed sized vector of numbers that can represent any sentence. And what that's allowed us to do is, now that we have a single way of representing text, we can perform many, many different tasks by using the same representation. And that's actually like a huge breakthrough in the field, was this idea of being able to represent any piece of text using the same vector representation. And even though it's not understandable to us, we can train machine learning models on top of this representation that can do the classification tasks that we want it to do. For example, like predicting whether an email is spam or real email, in addition to many other tasks. Some of the other considerations are, what are the possible, basically what's the model that we're going to learn? So if in a machine learning model, it has a predetermined number of parameters, different numbers that it can tweak in order to adjust what its final prediction is. And based on how much data we have or how much time we have to train this model, we may want to add lots and lots of parameters. There are models today with billions of parameters. But if we only have one computer and a very small amount of compute budget, then we're probably not going to be able to train a model that big. We're going to have to use a much smaller model. So our hypothesis space, the possible parameters that we're going to use for this machine learning model, becomes much smaller. We also have to consider what kind of signal do we have? Do we have labels like in this spam versus ham example? Or do we only have some final final label, like in the chess or checkers game, where all we know is whether we won or lost? That's really the only signal that the main signal that we get that really tells us how well our model did. And there are also delayed labels, like in the stock analysis. If we're trying to determine whether our model is doing well, we're not going to know until 5 minutes from now, once we get the feedback of whether our model predicted it correctly. Also, we have to consider, so how are we going to update the model? There's many different types of learning algorithms that exist. And finally, we have to look at the evaluation. We have to say, based on what the task is, how are we going to evaluate whether a model did well or not? And based on how well we did, is this good enough for us? Do we need to continue learning? Or is this enough? Is this, we have some level of accuracy, we want 99% accurate, and that's good enough for us. The extra 0.1% that would take another 10 days of training a machine learning model may not be worth it for us. So there are a lot of things to consider. And when we talk about machine learning, there are a few, there's the main types. There are kind of some subsets of these, but these are kind of the 4 main types of machine learning. And I've alluded to each of these in some way or another, but to make it very explicit, the 4 types of machine learning that we generally, the 4 types that we have supervised learning, where this is the spam versus ham example is a very classic supervised example of supervised learning, where we have labeled training data. It's not that we have experiences. We have data where there is an input to the machine learning model, and there's an output to the machine learning, sorry, not an output, but a correct label. There's an answer, basically. And the way that this type of learning happens is, we've kind of gone over this. You give them, the learning algorithm, all these examples, and for each example, we're going to put as our input to the machine learning model, the input, the data itself. And what we want to see is how far away from the ground truth label is our machine learning model's predicted output. So that's that's supervised learning. And in semi-supervised learning, maybe it's very similar to supervised learning, except now maybe we have some unlabeled data, or maybe we have a large amount of unlabeled data, but we only have a smaller amount of labeled training data. And this is actually a very real world situation to be in, where it's actually very expensive to gather labels for training data. Imagine if you're on your own, if you were going to sit down and label emails, whether they're spam or ham, it's going to take hours and hours, and you're probably going to only end up with maybe a few thousand examples at the most. And for some machine learning models, that's very, very few. But oftentimes it's very easy just to gather emails. You just go online and you look up, some database that has emails, and maybe they're free to download. And this is a very common example. And some things that you can do with this semi-supervised learning is you can train a model on your few labeled examples, and then have your model predict the outputs for all these unlabeled examples. And then in an iterative process, what you're going to do is you're going to see, okay, of the predictions where my model was very confident on the unlabeled data, it was very confident that its prediction was correct. I'm going to incorporate that into my original labeled data. And now I can train a new model on a larger amount of labeled training data with some slightly smaller amount of unlabeled data. And now all of a sudden you can iteratively increase the amount of supervision that your model is getting. And in general, that's going to improve the performance. Another major type of machine learning is reinforcement learning. And this is chess or checkers are very stereotypical examples of reinforcement learning, where only occasionally are we going to get feedback. Supposing at the end of the game, we know whether we won or lost. And usually it's not going to happen immediate, right? It takes time. We have to play through the whole game until we actually know whether we won or lost. And even if we thought, as humans, we would think, oh, well, maybe I captured my opponent's piece. That's a positive. But you can't necessarily make that assumption, especially in chess or checkers. Sometimes you want to lure your opponent into taking one of your pieces in order for you to make a better move in the future. So you can't necessarily assume that there are some intermediate bits of feedback, even though we want to. And then unsupervised learning is this last type of machine learning that I haven't touched on at all, I don't think. And generally, unsupervised learning it's going to be our task when we want to learn a little bit more about the data itself. We're going to try and learn, okay, maybe there's some commonalities among the data that we can group different pieces together. So actually, this is applicable in the spam versus ham task. We're supposing that we have no labels at all. Maybe there are some commonalities among the spam emails that we can see, that we can find. Things like words that have a number in the middle of them, maybe. When we can group those, or we can pull those away from the rest of the emails, we can see that's some feature about the data itself that allows us to draw some insight from the data. Also, oftentimes we represent this data, or some of the data itself is very high dimensional, or it doesn't lend itself very well to us to be able to really visualize it. So dimensionality reduction becomes very important when we want to be able to look at the data, and maybe we're going to be the ones who draw some insight from it by reducing the dimension to either 2 or 3 dimensions, so that we can graph some data, we can plot it, and see maybe there is some structure to it that we would like to find. And these 4 different types of machine learning problems kind of can be split up a little bit more into whether our outputs are either discrete or continuous outputs. And that kind of leads us to this nice little box that describes some of the different types of machine learning problems, where if we have labels, we're in the supervised learning column. And so if our categories, or if our labels are categorical, so in the spam versus ham problem, that would be a very common example of classification, where it's actually a binary classification task. But it's also possible that we have a multi-class classification task. So try to think of it. Supposing that we have news articles and we want to classify these into what the topic is. We want to say this article is about sports, that article is about politics, this article is about weather. So there's all kinds of different classification tasks that would fall under the supervised learning category. But we also have some supervised learning tasks that don't have categorical labels. Maybe they have continuous labels. So this would be something like trying to predict the value of a house. So if we know how many windows and how many bedrooms and what's the area code of a house, the output itself isn't a yes/no question. It's not a category either. It's going to be a number, anywhere between negative something, negative infinity, and positive infinity. Realistically, it can't be negative, and we know that it's not going to be infinite, but it could be very high. And we don't know what the upper limit is necessarily. And then the other 2 types of problems in the unsupervised learning side would be if we know that there are going to be some finite number of groupings of our data, then we would call that, it's part of clustering, but we would say that this is now a discrete learning problem, where we say that, okay, we think that there's supposed to be maybe 5 clusters within our data, and we just want to see what's the best way to fit this data into 5 separate groups. Or as I talked about before, if our data is, or if our task itself is not to necessarily group things into separate groups, but rather we just want to be able to represent this data in a graph that we can visualize in 2 or 3 dimensions, then we just want to be able to reduce the data itself to a continuous vector, but in smaller dimension than what it originally is. Um, and we can look at some of the examples of these different tasks. So in classification or labeling, right, and one example would be object detection, where we want to say, okay, we have some image and we're going to say, we're going to try to find the outline of each piece. So for example, this is the building over here, and we want to say, where does the building start? Where does it end? What other objects are in this image? Or we have, as I explained earlier, we have clustering, where supposing that we have a bunch of data, we want to find out what is the best way to group our data into 3 separate groups. And that would generally be, it's a type of task where we don't necessarily know that there are 3 groups, but we can run the algorithm, this learning algorithm, by saying, oh, this time there's 3 groups, and then we can rerun the algorithm and say there's 4 groups now, and then we can do it with 5 groups, and we can analyze the results and see which really fits the data best. And that's a way of drawing insight from this data of saying, okay, there's maybe we thought that there's only spam and real emails, but actually there's kind of this third category that maybe falls somewhere in between them. And through this clustering algorithm, maybe we would learn that. Or we can look at regression. We can see, hey, we have a lot of data about these houses, and we just want to predict what's the value of the house based on all of our features. Or again, when we're talking about unsupervised algorithms, if we're looking at dimensionality reduction, the goal here is really to try and draw some insight from data. So supposing that our data is actually, a 100-dimensional vector, and we have thousands and thousands of data points, we can't really, there's not much we can say about something that's 1,000 dimensions. So, if we visually look at a vector, a written vector on the computer, and 1,000 numbers for just for one thing, and we're supposed to look at thousands of examples of those, we're not going to be able to pull any insight from that. So we need to be able to reduce the dimension. And actually some techniques can help us not only reduce the dimension, but the goals are to preserve some of the structure, the global structure or the local structure of the data itself. And sometimes you get very nice structure that can be visualized in 2 or 3 dimensions. And oftentimes what happens is that really you want to reduce the dimension, and then maybe you do some clustering after that, or you do clustering first, and then you can reduce the dimension of your data. And these often are used actually in conjunction. So the typical way that we actually, the learning algorithm itself, the way that we train the machine learning model and we test it, happens in a few different phases. We usually divide our data into 3 different subsets, sometimes only 2, but the 3 different sets that we're going to split our data are usually into training data. This is data that that the learning algorithm is going to use to determine what are the weights for each parameter of our machine learning model. Right? So a machine learning model is made up of hundreds, thousands, could be billions of parameters in modern models. And all it is just a whole bunch of linear algebra where the input is some vector or a series of vectors, and our model is going to, through a bunch of multiplications and a few other operations, is going to percolate the numbers up through the machine learning model through a whole bunch of different layers, and at the end it's going to make a prediction. And this training data is going to be what we use in order to update all of those weights in the model itself. So it's the learning algorithm is going to give all the inputs to the model. The model is going to make a prediction, and we're going to see how wrong was the prediction. And then we're going to be able to use linear algebra and some calculus to be able to to be able to adjust all of our weights so that the next time we see this exact example, we're going to make the correct prediction, or at least a better prediction. And so that's what happens during the training. But then the question is, so how do we know that this model, even though maybe it's trained very well and it gets 100% accuracy on our training data, how do we know that's going to be able to generalize to new data that it hasn't seen? And that's where validation and testing data come into play. Validation data is generally used as a way to determine some of the parameters for the learning algorithm itself. So how much do we want to move the weights from the machine learning model at each iteration? For each example that our model sees, how much do we want to move the outputs? If we move them 100% to the correct answer every time, then we're going to completely forget what we've previously learned. So we don't want to do that. We actually want to not learn too quickly. We kind of want this to be a slightly more slow process. And that's what the validation data does. We can train on the training data. We can learn a model. Maybe we go through all the training data one time. Maybe we go through the training data 2 times. Maybe we go through the training data 3 times. And then we're going to use this separate validation data to determine which of those will do best on this held out set of data that we haven't trained on. And that's going to give us a good idea of how well do we do on our testing data, which this testing data is meant to emulate what the real world situation is, our actual, the data that's possibly very different from training data, but likely somewhat similar, but a little bit different. And the idea here is that we're going to train multiple models. We're just going to determine which of those models does best on some unseen amount of data. That's the validation. And then our actual determination of how well did our model do is that we have a third set, this testing set of data, where we're just going to see how well did this best validation model do on the testing data. And this is generally how things are done, but sometimes you actually have a specific training budget. Maybe you can only train your model for a specific number of epochs or epochs, or only a certain number of examples that you are allowed to see. And so you're going to go through a slightly more iterative process where you're just going to say, hey, I've trained for however many examples, and you produce a model, and you're going to say, is this above some threshold of goodness? If yes, okay, great. That's it, we're done. If not, continue to train. These are kind of the typical ways where we actually train and test the machine learning model. And as I said before, sometimes it's only 2 different subsets of data. Sometimes it could just be training and testing. And oftentimes that's because it's just what do you call it? It's just a side effect of how much data do we have. If we don't have very much data, we probably aren't going to set anything aside for validation because we really want to use that for training as well. So that's kind of the big picture of how does machine learning work, and just to kind of touch on just some ways that machine learning exists in the real world and how this is kind of starting to become part of society and how people can get into it. So for people who aren't familiar, Kaggle is this website that has tons of data sets, lots of different competitions that they hold, new competitions where they have prizes, and companies can put out monetary prizes to get people, just regular people who aren't necessarily, it's not a job, it's just a hobby, people who enjoy gaining insight from data. And Kaggle is a place that hosts these kind of competitions. And once competitions are done, many times, the data sets that maybe a company or whoever it is that hosts the competition, they leave the data set available to the public for people to use. This is a really good resource, actually. It's great for people who are trying to get started in data science or machine learning. And it's, as you can imagine, if you were trying to train a machine learning model for some new task, you would have to go out and gather lots and lots of data. And that's a really it's a huge burden. One person would not be able to do that for a large amount of data. And so Kaggle and there are other websites that do similar things are really good resources of data and good ways to get started and just to try things out. Similarly, if you can find loads of different blogs online of ways, just different resources of people who talk about machine learning, and not just in like the hype and what new thing came out just now, but really to get in depth and learn how these learning algorithms work and how to train models and what data sets to use and what to look for in data and what makes some data good and bad, or all kinds of things. There's loads of different blogs and different websites that have all kinds of data. And Katie Nuggets is just one example. Some other just examples of places where machine learning has been used in the real world, or I would call it, just in it's expanded beyond just some small little subset of computer science researchers. So it's started to become much more real in like the mid to late 2000s. One example of that is the Netflix prize, where Netflix actually put out a competition, essentially the same way that Kaggle does it, where they put out data for groups to use and gave kind of a threshold that they wanted people to be able to achieve. And if anyone achieved that, then they would win this $1 million grand prize. And it was actually awarded in 2009. And there's loads of other times and ways that machine learning has kind of started to become a much more realistic way to solve problems instead of people deciding how to what are the important features. We've started to shift towards this idea that we're just going to gather a whole bunch of data and we're going to let the machine learning model and the learning algorithm itself determine how to pull out the important features from data. And that shows in all kinds of different robotic challenges that some government agencies have put out, like the robotics challenge, and IBM this is actually in the 90s that they put out Deep Blue, which was a chess playing program that was able to beat, at the time, the world chess champion, Garry Kasparov. And I have a whole bunch of other examples, but I think we should leave some time for questions. Of course, keep talking.
Hi, I just want to mention that usually if you want to open it up for questions now, I can, but then the recording has to stop because, so if you want to go on with a couple more examples, we usually run it until 7 and then open it up for questions.
Okay. I thought it was only 6:45. Okay, cool. All right, well then I'll keep going. So some other examples, more recently, so the few examples I've given already were in the 90s. Maybe these ones are in the early mid 2000s. Getting closer to us, AlphaGo was this program that came up at DeepMind, is the company in Britain that developed this program that was able to play Go. And Go is, for people who aren't aware, I've never played, but is a very, very complicated game where in chess for Deep Blue, I don't know the number of moves, but maybe it's a few million possible board configurations that can happen. But in Go, it's orders of magnitude more possible configurations on the board. The different ways that the pieces could have been played is just huge, and it's the way that Deep Blue worked was a lot of it was rule based. It was just saying, hey, if this is the situation, make this move. If that's the situation, make that move. But when you start getting to Go with millions and millions of possible moves, you can't write a rule for each of those. You have to have a learning algorithm that's able to draw some insight from games that it's seen and be able to generalize some of the moves that it's seen in the past to new moves that maybe board configurations that it wasn't able to see during training. And so what they used was actually some deep neural networks in combination with some human games. So the way that it worked is that the machine learning model saw some human games, and that gave it kind of a baseline of what learning to predict what moves are good moves, but it wasn't great. It's not a lot of examples that it was given. And then beyond those few examples it was given, it learned through self-play, or basically what it is just that you have two machine learning models or it's even one machine learning model that's just replicated and they play against each other. And through this self-play, it's able to learn what was a good move, what was a bad move. And just through this, a lot of self-play, DeepMind was able to get a machine learning model that was able to beat the top Go player. This was in 2016. So that's a really, really impressive application of machine learning. Another example is IBM's Watson. So for people who aren't familiar, this was a machine learning model that essentially listens to spoken language, right? So when Alex Trebek would ask a question on Jeopardy, players can hear the question, they understand what Alex is asking for, and they're able to retrieve from their mind some information that they think is a correct answer. And it was a huge challenge actually for machine learning models because, well, machines don't understand human language unless you give them a way to, right? The only way that we can communicate with computers right now is mostly through a keyboard. We can type in something, open this program, or with a mouse where we move the cursor on the screen and we click on something, and that's how we can interact with the computer. But with Jeopardy, there was this whole other issue of how can you get the computer to understand spoken language. And understand the spoken language in a way that it knows what the question is. It has to understand the words in the question. It has to understand some nuances of language, like is this a pun? Is there a rhyme that's happening? Is there some sort of extra hint that's happening in the question? And then once it's able to understand that, it even had to go further, and it's not just that it understands it, but it has to be able to retrieve a correct answer for whatever the question was. Or actually, it's the opposite. It has to be able to retrieve the question for the answer. So as I've kind of been alluding to, it takes a few different capabilities, right? So it has to understand language. It had to be able to try and think of, okay, so what does it believe is the correct answer or the correct question to answer? And then beyond that, it's going to continue to learn based on its own experiences, actually. And actually, can you guys still see the screen? I hope so. This is an example of machine learning that was used in robotics. So this is, for people who aren't familiar, Boston Dynamics is a company that builds robots, and they use machine learning to get their robots to be able to interact in the real world. This is just an example of how that's been used. Okay, so what we saw, hopefully you guys are seeing this, is the first robot comes up. Okay, this is orchestrated. This isn't a lot of machine learning, but there is some. But we see the first robot shows up. It doesn't have any way of opening this door. It waits for its buddy, who does have an arm and can open up the door. But what I really want to show you guys is this other example, where now they're adversarially challenging this robot. The robot doesn't know what the person is going to do. This person is just getting in the way of the machine. And the machine has to overcome this. And this is a really, really good example of the idea of like generalization. For the first example, for this first video, we saw it's orchestrated very well. Nothing out of the ordinary happens. The machine could have just been programmed to do exactly that, and nothing would have gone wrong. But now, what they've done is they've introduced a person to increase the complexity of the environment that the robot is in, and all of a sudden the person is going to get in the way of the robot. It's going to, in a second, it probably the person tries to close the door. And this is where machine learning really comes into play. It's dealing with trying to overcome some unknown things that can happen in the real world, especially in robotics. There's a lot of unknowns. You don't know what the terrain is going to be. You don't know where other people are going to be at any given time. It's a very open environment, and they have to be able to overcome that. So let's continue with this. So let's see if we're that. Yeah, so a lot of unknowns. It wasn't like the model, a machine learning model was trained with, a person pulling on it or something like that, or with the person closing the door. These are, maybe it was able to see a few examples of that, but not this exact configuration of the angle that the person was pulling at and how much force they were using when they're pulling. This is a really good example of generalization that's very important in machine learning, and is one of the reasons why machine learning is so prevalent today, is that it's able to handle these unknown examples. So to kind of end this off, so what is machine learning? Machine learning is really, we're going to combine some algorithms, some programs, or some systems along with data. And what we want to do is we're going to combine those two. We're going to have an algorithm that uses the data to learn a model that is able to generalize to unseen experiences. It's going to be able to improve by getting more data, and it's going to be able to adapt to whatever new situation. Ideally, it's going to be able to adapt to new situations that it hasn't seen during training. I think that's probably a good place to end off at. I think that's.
Thank you so much, Alon. Am I pronouncing your name correctly?
Yeah, Alon. Yep.
All right, thank you, Alon.
Yeah.
It looks like you have some questions here, and you can either read them or it can be read to you, and then you can provide an answer. If you can see the Q&A, they're all in the Q&A. And I will stop recording at this point once we start with the responses to the question. And thank you so much for your presentation. It was very nice.
Yeah, thank you. Thanks for having me. Yeah, I'll read them out. So actually, yeah, sorry, I didn't have the Q&A or the chat open while I was presenting. It's really hard to have in the Zoom.